What specific problem does the Dolphin model aim to solve in the context of on-device language models, and why is it significant?
The Dolphin model specifically aims to address the challenges of energy consumption and processing speed associated with handling long contexts in on-device language models. This is significant because mobile devices often face critical battery life constraints, and complex language processing tasks can quickly deplete power resources, limiting the practical utility of AI applications. By employing a novel decoder-decoder architecture that compresses extensive contextual information into memory tokens, Dolphin achieves a 10-fold improvement in energy efficiency and a 5-fold reduction in latency compared to traditional methods. This innovation not only enhances the model's ability to process longer contexts without incurring typical computational overhead, but also maintains high accuracy in understanding and generating responses. Ultimately, Dolphin's advancements are crucial for deploying sophisticated AI capabilities in resource-constrained environments, such as mobile computing and IoT devices.
How does the Dolphin model's decoder-decoder architecture work? Please illustrate the step-by-step process of how context is processed and utilized in this model.
The Dolphin model employs a novel decoder-decoder architecture that processes long contexts efficiently by conceptualizing them as a distinct modality. Initially, the context C is input into a smaller decoder, pi_s with 0.5b parameters, which compresses the context into a reduced embedding representation. This compression significantly decreases the embedding size, achieving a compression rate, ρ, of up to 8, thus alleviating the computational burden on the larger decoder, pi_l with 7b parameters. The compressed embeddings are then transformed into context token embeddings using a projector, phi, implemented as a multi-layer perceptron, MLP, which aligns the dimensions of the embeddings for input into pi_l. Finally, the main decoder, pi_l, processes these embeddings along with the user's query, Q, to generate a coherent response, R, effectively utilizing the condensed information from the long context while maintaining high accuracy and efficiency.
Can you provide a simple example that demonstrates the inner workings of the Dolphin model, explaining how the smaller decoder compresses the context before passing it to the larger decoder?
The Dolphin model employs a two-decoder architecture, where the smaller decoder, denoted as pi_s with 0.5b parameters, compresses the long context before it is processed by the larger decoder, pi_l with 7b parameters. For example, if we have a long context, C, of length, L, the smaller decoder, pi_s, first transforms this context into a compressed embedding representation, reducing the size to n tokens, where the compression rate, ρ, can reach up to 8. This means that instead of directly inputting the entire context into the larger decoder, which would require processing L times 3584 embeddings, the model only needs to handle n embeddings after compression. The compressed representation is then passed to the larger decoder, pi_l, which generates the final response, R, based on the reduced input, significantly lowering the computational burden and improving efficiency while maintaining the quality of the output. This innovative approach allows the Dolphin model to effectively manage long contexts with enhanced energy efficiency and reduced latency.
What are the theoretical advantages of the Dolphin model regarding energy efficiency and latency compared to traditional LLMs?
The Dolphin model offers significant theoretical advantages in energy efficiency and latency compared to traditional large language models, LLMs, through its innovative decoder-decoder architecture. By utilizing a smaller 0.5b decoder to compress extensive contextual information into memory tokens, Dolphin reduces the input length for the primary 7b decoder, which minimizes the computational burden and energy consumption associated with processing long contexts. This approach results in a remarkable 10-fold improvement in energy efficiency and a 5-fold reduction in latency compared to conventional methods that process full-length contexts. Additionally, The model's ability to treat long context as a distinct modality, akin to vision language models, allows for more efficient handling of information, further enhancing its performance in real-time applications. Overall, these design choices enable Dolphin to maintain high accuracy while significantly optimizing resource usage, making it particularly suitable for on-device applications in resource-constrained environments.
How did you validate the effectiveness of the Dolphin model? Describe the experimental setup, datasets, and performance metrics used to assess its capabilities.
To validate the effectiveness of the Dolphin model, we conducted a series of experiments using a comprehensive testing dataset comprising 3,740 context prompt response samples derived from the prompt with context (PWC) dataset. This dataset was specifically selected to include context lengths of less than 512 words, aligning with the model's maximum context length. We evaluated the model's performance across 6 question categories: contextual QA, numeric QA, rephrasing, summarization, title keywords, and continuation. Performance metrics included latency and accuracy, with the Dolphin model achieving an average latency of 4.32 seconds, approximately 4.79 times faster than the baseline Qwen 2-7B model, and maintaining high accuracy rates, such as 100% in title keywords and continuation categories, and over 98% in numeric QA. These results demonstrate that the Dolphin model effectively balances speed and accuracy, confirming its potential for energy-efficient, on-device language processing.
What key results did the Dolphin model achieve in terms of latency improvement and accuracy? And how do these results compare to existing models like Qwen 2-7B?
The Dolphin model achieved a significant latency improvement, with an average latency of 4.32 seconds, which is approximately 4.79 times faster than the Qwen 2-7B model's latency of 20.71 seconds. In terms of accuracy, Dolphin maintained high correctness scores across various question categories, achieving perfect accuracy rates of 100% in title, keywords, and continuation categories, and high scores of 97.76% for contextual QA and 98.53% for numeric QA. Notably, despite utilizing compressed tokens, Dolphin demonstrated comparable performance to Qwen 2-7B, winning 23.6% of comparisons and tying 44.2%, resulting in a combined win-tie rate of 67.8%. This indicates that Dolphin's compression techniques effectively preserve and potentially enhance the capabilities of Qwen 2-7B while reducing computational requirements. Overall, these results underscore Dolphin's potential for energy-efficient, on-device language modeling, particularly in resource-constrained environments.